Good morning, students. In the last class, we saw about how decision trees, the creation of the decision tree is, and the major important steps, how we can create a decision tree. Okay. So with that, basically, every time as we go ahead with, right, we first solve a problem and then go ahead with the algorithm. So today we will discuss about the algorithm, and the algorithm is over here. So the main steps in decision trees are the step one was identifying the entropy or calculating the entropy of the entire given data set with the formula minus p divided by p plus n into log 2 of p divided by p plus n minus n divided by p plus n into log 2 of n divided by p plus n. So this is about the entropy. Once we calculate the entropy, next we immediately calculate the average information of each and every attribute in the given table. So each and every attribute in the example that we saw was we had outlook, we had humidity, you had windy, and we had the temperature. So all the four attributes separately we are going to calculate its average information. Okay, so that average information is being calculated by considering each and every attribute. So when I tell outlook, right, so in the outlook we had three parameters coming into picture, right? It was sunny, rainy, and overcast. So all the three we created separate tables for them. From the separate tables we calculated what are the number of positives and what are the number of negatives, and after calculating the positive and negatives we substituted and we calculated the entropy, right? So each and every a value of the entropy was taken with respect to a summation of it. Summation of P of sunny plus N of sunny divided by the total number of P plus N into entropy of sunny. A similar way with rainy and the overcast. So with the over average formula of it, we got the average information of entropy with respect to outlook. Again, we calculated with respect to temperature, we calculated with respect to humidity, as well as with respect to windy. The third step was calculating the gain. The gain formula was entropy minus the average information entropy gave us the gain value. The highest gain, the highest value with respect to which attribute, that attribute was picked up as our root node. So this is what the procedure that we have seen from our previous classes. Now we directly go into the algorithm and see what this algorithm is about. Okay, algorithm, how do we write this? So ID3 algorithm, what are its input parameters that is required? One is the training samples, which is nothing but the examples over here. So we have the examples, the target attribute, and the attribute. So there are three keywords that we're using over here. So one is the examples, the target attributes, and attributes. Let's see what each and everything does. Okay, examples are the training examples. Remember the initial data set that we had, right, with 4 parameters, and the final output is play tennis. Let's consider that entire tabular column to be as our training samples with each and every input space given. Okay, so that is our training data. The target attributes are the attributes whose value is to be predicted by the tree. Okay, target attributes are the attributes whose value is to be predicted by the tree. Okay, we're going to tell there, right? Okay, this attribute solely can predict the output or can classify the given data. Okay, so that is going to be the target attributes. What is the attribute? Is the list of other attributes that may be tested by the learned decision tree. So if I give some other training or the testing data for it, right? So attributes tested by the tree. If I give a tested data, how it is exactly going to predict the given output. Okay, so there are 3 values for that. The keywords, the examples, the target attributes, and the attributes. Okay. What does it return? It's going to return a decision tree that correctly classifies the given example. The main focus of us is like when we construct a decision tree, our decision tree, when it is given or with a tested data, it should actually correctly predict whether the given data is correctly classified or not classified, right? So the correct classification of it, the predictive data is more important. So it is telling it's going to return a decision tree that correctly classifies the given example. How do we start it? So the first step is you have to create a root node. As we have already discussed, we have to create a root node. By performing the 3 major steps, the highest gain value is going to be picked up as our root node. Okay, so that we do it. Create the root node for the tree. If all the examples are positive, return a single node tree root with label plus. If suppose I have all the play tennis value as yes, okay, then I'm going to take one single node with that particular tree and make it as a root node and give it as a positive label. If all the examples are negative, so if I have everything, the play tennis value is completely no, then I'm going to take one of the node, okay, single node tree root, and I'm going to label it as minus. So it indicates that the entire tree is a negative. There's all the samples with respect to negative, okay. If the attributes are empty, okay, return the single node tree root with the label most common values of the target attributes in the example. Okay, if the entire attributes are going to be empty, in the topmost, like the target attributes like the temperature, the overcast, the windy, or the the humidity. Okay, so the four parameters, whichever has most commonly occurred, we are going to take that attribute and just give it from the example. You're going to take that attribute and give it to be as the root node. Otherwise, what do we do here? This is how we actually try to create our tree. So I'm going to take, let A, okay, A, the attribute from the attributes that best classifies the example. See, we already told attributes, we had four things there, right? So we had one is the temperature, the overcast, outlook, temperature, humidity, and windy from the table. Okay, so these are the four attributes that we have. So each and every attribute from the the capital attributes, okay, from there, that best classifies the example. How did we get to know that best classifies the example? Because we calculated the gain parameter, and the gain parameter told us the highest value of it. So which means that it is going to best classify the given data set. So I'm going to take that attribute A. Okay, and what I do, that decision. So in this example, the first case, whatever we got was the A value was outlook. Okay, we took the outlook because outlook was our decision, that is the root node that we considered, right, while constructing the decision tree. So this becomes A, becomes the outlook. So the decision attribute, okay, for root is going to be A. I'm going to assign that A to outlook. So here in the right hand side, I've written a small diagram which you can easily understand, okay, what is this exact flow of it. So as I told, outlook was our root node that we constructed, right? So A is going to be the outlook. Okay, and for each positive value for each positive value, whichever the instances that we have, right, vi, what was that vi? When I told about the outlook had three important features, right? One was sunny, rainy, and overcast. So all these three becomes vi. So let me annotate you for that. So when I consider, this was basically my outlook. Okay, so this is my outlook because my gain was more with respect to the outlook attribute. Okay, and then I told that for each positive of vi, outlook had three values. One was sunny, and the other one was overcast, and the other one was rainy. Okay, so I have these three values, right? For each positive, because we're going to consider, right, we're going to take those positives and negatives of it for each positive value of vi. Okay, when I tell sunny, I'm going to take it. Okay, add a new tree branch below the root corresponding to the best A is equal to Vi. That is what I have done. So when we saw in the example, we had something like this, right? So when I took the entire data set, so the first column was with respect to outlook. Okay, so when I took outlook, I had the values of sunny, okay, rainy, and overcast, right? So these three values, because now I've created my root node, which is the outlook, now I have to create its branches. I have to create the tree, right? I have to create the branches. So when I have to create the branches, I know these are the three values I'm going to get. So I'm going to assign one with sunny, okay, one for rainy, and one for overcast. Okay, so I did it. And let examples, okay, next step is let examples vi be the subset of the examples that has value vi for each. I mean, which means that we're going to consider the entire examples, that's the training data set with respect to vi, right? See, if examples vi is empty, right now we do not have empty, right? We have the entire given data set to us, right? It is not empty. So then what we do then, below this new branch, add a leaf node with label most common value of the target attribute in the example. So the target attribute in the example over here in case, as I told in our previous example, when we solved this, right, we saw that with Outlook, everything was yes. So we created a child node for that, right? Why did we create a child node and why did we create yes for that? Because all of these instances with respect to Outlook had a value of S. There was no negative at all. There was no value called as no in it. So it was all positives, right? So since it has all positives, okay, we are going to take the most common value. Yes, all the values that we got was the yes, okay, from the target attribute. Which was the target attribute here? Yes or no is the target attribute. As we specified earlier, it was yes or no, the target attribute. Okay. In the examples, yes, in the examples play tennis, it has only yes or no. You do not find anything else. Okay. So we are just directly going to create this child node or the leaf node. Yes, because based on the common values of it, okay, we're going to add it. Fine. Else, if it has a mix of it, okay, if it has a mix of it, then what do you do? Below a branch, okay, now I'm going to add below a branch. The branch for this is yes, with respect to Sunny, yes, okay. And again, I'm going to create a subtree. If you remember, okay, from the root, we did the first three steps, we got the root node. Once immediately after we got the root node, we created separate table, okay, separate table. One was with respect to only the Sunny values, okay, entirely Outlook, temperature, humidity, windy, and play tennis. We had this, right? Play tennis. Okay, this was one. On the other side, we immediately again created one for rainy. All we considered only the values for rainy. Okay, the same Outlook, temperature, humidity, windy, and play tennis. So we constructed new tables, and again from there we started the same procedure of creating the decision tree. We came up with, okay, what is the other next decision node that is required over here? And we saw that with respect to Sunny, we got a value of humidity, H. With respect to rainy, we saw it was temperature or windy. We saw it was windy. Okay. Then we had created two more of it, and finally either yes or no with respect to weak or strong. And again, here humidity, high or normal. Okay. We entirely created the decision tree, right? So which means that after one stage, if you do not find anything with respect to the leaf nodes, once you have encountered it, the remaining is you're again going to give, okay, all of these parts. Now you're going to give it to a creation of the new decision tree. Again, you're going to create again from this. We are going to create the left hand side and the right hand side. We are going to create one after the other. That's what we do it here. You can see ID3. So I'm going to add a subtree. As I told from Sunny, we are going to add another subtree. So add a subtree ID3. Okay. Examples are my training data. Okay. With respect to VI. Yes, VI over here is with respect to the parameters that it has. The parameters was here, the sunny, overcast and rainy. Overcast is already done. So I only have sunny and rainy remaining. So I'm going to create two separate tables like this, and I'm going to start my construction of the tree, right? So for that, what I did, I gave the training examples with respect to VI. VI is the sunny and VI with respect to rainy. So I've given all the data for that. And the target attributes of it, yes, what was either the yes or the no category of each and every instances, we had given the data for that. And I have the attributes. What are the attributes for that? One was with respect to overcast, with respect to sunny, but we had the temperature, humidity, windy, and the play tennis, the complete instances we were giving it, right? And you can see minus of A. What is this? Right here, A was my outlook, okay? I just have only with respect to that, all the remaining other attributes I will be using to construct the decision tree. Okay, because A I've already created as a root node, but from there I have to construct the remaining trees, okay, the subtree of it. From outlook, one with rainy, one with respect to sunny, I'm going to create separate trees. I mean, it's a branching of it. I have to create the subtree for that. Okay, so I'm going to do it with it. So if you can correlate each and everything with the above example that we have solved, this easily gets into our mind, okay, how each and every step is being taken. From what step next, what should I do? So we can have a correct flow of it. Okay. So to just give you a very quick recap on this, so we'll just consider the major steps that we perform. So as I told you, the steps that we actually consider with the decision trees are the three major steps: calculation of the entropy, the average information, and the gain. Right. So the entropy of the entire given data set is being calculated by using the formula minus p divided by p plus n into log 2 of p divided by p plus n minus n divided by p plus n into log 2 of n divided by p plus n. That's the first entropy formula calculation. Then from the given table, we take each and every attribute out of it and we calculate the average information of that attribute. Okay, how well that one single attribute can solely contribute to classifying the given training data. Okay, so in that case, what we did, we calculated, okay, for each and every attribute, we calculated the VI values of that. So when I took Outlook, the VI values for that was sunny, rainy, and overcast. When I take temperature, it is hot and cold. When I take humidity, it is high and weak or strong and weak. Okay, so we had the values, right? So all of those feature values, okay, we will be considering that to be as VI with respect to the algorithm. Then immediately after that calculating, we calculated the gain value of it by considering the information minus of the average information with respect to that particular attribute. Okay. So when we did that, we get the gain value. So we calculated this for all the attributes, the four attributes that we have in the current table. We saw the highest value that has with respect to the gain that was being picked up to form the root node, and the root node was considered over here. Okay. A is the value of the attribute that best classifies the example. So that a value, that attribute value that we're going to consider is the outlook. Okay, so what we did, we started construction of the decision tree by considering the root node, which is the outlook. So once we started going ahead with that, with all the positives with respect to VI, if in case, okay, if there are all the common attributes, suppose all the values are yes in it, so we try to check out if there are any child nodes in it or the leaf nodes in it, and we observe that overcast had all the values of yes, so we directly formed it as to be as a leaf node. Okay, after that, what we did from the root node, okay, we are trying to construct the subtree of it. So in order to construct the subtree of it, basically we constructed two branches for that, because Outlook has three VIs. Okay, the value of it of VI was three, that is the sunny, the overcast, and the rainy. So from these three, now we created three different branches, and in that one became the overcast, that is the child node. Okay, remaining we have two. So we have to create another subtree for that. So what we did was we only considered from the given table all the sunny values of it was created into another table. All the rainy values of instances were created into another table. From there, we started again performing the same calculations as that of the ID3, right? We calculated the entropy, we calculated the average information, and again the gain. Okay, highest value of it then was created as a decision tree, which means that you're reconstructing the same ID3 subtree. Okay, so in order to do that, we use the same ID3 of the training data with respect to VI, yes, only the sunny data and the rainy data, and the target attributes, basically the yes or no values that it was there, and the attributes are the overcast, the windy, the rainy, the overcast, temperature, humidity, and windy. But since overcast, we have all outlook, we have already taken it out that. Okay, when we have already removed the outlook, the other three parameters is what we give the attribute, and we start constructing the tree. This is an overall about your ID3 algorithm. Okay, if you have any doubts, you can ask me. Okay, to continue with, okay, hypothesis space search in decision tree learning. We've already seen what a hypothesis space is, right? So all the given instances, okay, with respect to the training data, with respect to its target values, entirely forms a hypothesis space. Okay, how exactly with respect to decision tree, the learning of hypothesis is going to happen? So basically what this does here is the decision tree, okay, can be characterized as searching a space, okay, of hypothesis that best fits the training data. Basically we will try to find out one particular hypothesis that best fits our training data, right? So decision trees are also one among which can search all of these hypothesis spaces, comes up with one particular hypothesis that best fits the given problem statement. Okay, so it actually tries to come up with the target function such that it best fits the given solution, and whatever the correct predictions or the classification that is required is satisfied. Okay, so ID3 can be categorized as searching a space of hypothesis from one that fits the given training example. We saw that, right, with the given training example, how we constructed the decision tree. So now if I give an instance, okay, telling that today I think, okay, the temperature seems to be good, okay, I can give my own set of instance. When I give such an instance to the decision tree, it should correctly tell me whether I'm interested to play or not. Okay, that is the testing instance that I'm going to give to the decision tree. Okay, when I give the testing instances, basically it should come up with a solution for me. It should tell me, it should predict me whether whatever I was thinking, whether it was right or wrong. Right, so such a way in which it tries to search the given data and it comes up with a one that really best fits the given training example. Okay, the hypothesis space searched by the ID3 is a set of possible decision trees, as I told you, right? It's going to check all of its possibilities that it is there, and it is going to give you a classification, yes, whether yes, this is what was required. Okay, and it performs a simple to complex or a hill climbing search through this hypothesis space. Okay, it's a hill climbing search or a simple to complex, because it starts from the root node, then it starts widening up itself, right? So it has a wide tree. How you construct, based on the construction it will tell. So it is going from simple to complex, perform simple to complex, a hill climbing search, okay, through all of its hypothesis space. There are certain limitations with respect to decision trees. Okay, what are its limitations and its capabilities? Okay, ID3 hypothesis space of all decision tree is a complete space of finite discrete valued functions. This we have initially discussed in our previous classes, stating that, okay, ID3 basically it has a very finite discrete valued functions. Okay, it is very well suited for a discrete valued functions. Okay, so that basically means that we have the hypothesis space, which is all finite and discrete. Okay, it gives you, if I have to play today, if I want to play tennis today, I would check out the main criteria that is given, the features like the outlook, this the temperature, the windy, and the humidity. So I will tell, if it is rainy, I cannot play, right? So I'll give my instance telling that, okay, I want it to be sunny today, and the humidity, it is not too humid, so I want a weak or a very normal humid. Okay, and even the temperature not to be too high, and I will tell the windy, okay, a normal, I don't want a strong wind to come. Okay, a normal, a weak wind. Okay, so when I give all of these my test instances, right, it's mean it is very finite. Okay, I have, it's not a continuous value, it's a very finite value, sunny, rainy. No, it gives me a certain feature value for that, right? So ID3 actually works very well with respect to this. Okay, but ID3 avoids one of the major risks of methods that searches incomplete hypothesis space, because see, ID3 has a capability of overcoming these incomplete or inconsistent training data. Okay, it has a possibility of considering the error pruning technique or the rule post pruning technique, because whenever it finds out some of the data is missing or some of the data is irrelevant, right, it starts converting that as a leaf node and it continues with the other. Okay, like the error pruning or the rule post pruning. So it does not actually have that major risk with incomplete or inconsistent data. Okay, so these are certain features of ID3 algorithm. Okay, is there any limitations with ID3? Did you anywhere see, okay, how back propagation is done in this? Whether it is backtracking, whether it has come up with the right decision tree or not? Has anything, have you seen something with respect to the decision trees? So it's something which we have to look forward for. Okay, so ID3 maintains only a current one single hypothesis, as I told you, that best fits the solution, right? So only a single current hypothesis as it searches through the space of decision trees. It maintains only a single current hypothesis as it searches through a space of decision trees. Okay, whereas what in case of candidate elimination algorithm? Okay, it used to have a set of hypotheses. Remember, if we tell G and S value, the specific and the generic hypothesis, when we consider the generic one, it used to have the specific feature with everything as question marks, right? Okay, so it has multiple set of hypotheses, whereas ID3, it is just going to maintain one single hypothesis or a single current hypothesis as it searches through the entire decision trees. Okay, by maintaining only single hypothesis, okay, ID3 loses the capability that follow explicitly representing all consistent hypotheses. Yes, true, because in candidate elimination algorithm, we had those generic hypotheses that is created, right? We had a set of hypotheses for that. Here, it actually has only one single hypothesis and it loses the capabilities of explicitly representing all consistent hypotheses. Now, it is not going to tell you all consistent. It will tell me only one hypothesis at that current instance, but it is not going to give me all the consistent hypotheses. Okay. How many alternative decision trees can we create? Is there any information about that? We only created one decision tree for now. But is there any option that it can tell you how many decision trees are consistent? That's again a question mark for us. And as I told you, ID3 in its pure form, it performs no backtracking at all, okay, in its search. Not globally optimized, susceptible to usual risk of hill climbing. Okay, it does not perform any of the backtracking stuff. Okay, so ID3 uses all the training examples at each step in the search to make statistically based decision. When I just give one training data set, it will start branching itself to identify. Okay, but what it will do is it will have its entire training examples with it. So ID3, it uses all its training examples at each and every step in its search to make a statistically based decision. Okay, but how to refine its current hypothesis? Yes, obviously it will think about it, how it can come up, because as we told, ID3, it is going to come up with one particular hypothesis that best fits the solution. So it will start refining itself. This contrasts the finders and candidate elimination algorithm. We have seen, okay, what are the drawbacks of finders and candidate elimination algorithm? This is actually a contrast to it. Finders and candidate elimination, it takes only that particular instances of it and it fine tunes its hypothesis. Whereas here, the ID3 algorithm, it has the entire training examples to fine tune its hypothesis. Okay. One of the advantage, see, it's talking now about the advantage. One of the advantage of using the statistical properties, that is the information gain in our examples is, right, it is resulting, that it is basically resulting in much less sensitive to errors in individual training examples. So we saw how did we calculate the information gained, right? So we're going to take that information with respect to each and every attribute, how well only that attribute can solely classify the given example, or how can it only give the correct predictions with respect to that particular attribute. Okay, so one advantage of using the statistical properties, what was that statistical properties, the information, average information of each and every attribute, okay, is that the resulting search is much less sensitive to errors. Okay, this is one of the very major advantage. As you have seen, you have that additional step of it that we perform in each and every step of decision trees. Like we calculate the information, that is the entropy, the information, average information of each and every attribute, you calculate the gain, right? Each and every step we perform it. Okay, so that's one of the advantage with respect to the ID3. See, ID3 can be extended to handle the noisy training data. As I told, even if you have noise in it, based on the pruning and the rule prune technique, the error pruning and the rule prune techniques, it can actually try to handle the noisy data as well by modifying its termination criteria to accept the hypothesis that imperfectly fit the training data. As I told, there are circumstances or chances where it can perform that into a leaf node, or it can eliminate that data itself and continue with the next, okay, as if it has not occurred itself. So these are few advantages and disadvantages or limitations with respect to the ID3 algorithm. And here are a few definitions which probably will be very helpful for you when you look at when you're writing your exams with respect to ID3. So I just have noted few of the points over here which can really help you out with. The inductive bias in decision tree learning. Okay, what exactly does this inductive bias do, or how exactly can we consider this? Okay, it chooses the first acceptable tree it encounters, and it's very simple to complex or a hill climbing search through the given possible trees. Okay, as I told, we constructed one tree, right? Well, how did we do it? We performed, okay, by randomly considering, okay, which has a major gain value. We constructed that as a root node, and then we saw that, okay, how can we go ahead with branching? Is there any leaf node? We constructed the entire tree. Okay, that was the first acceptable tree for us. So we constructed that acceptable tree based on the simple to complex manner in a hill climbing approach. Okay, we started constructing that tree. What, when we construct that, there should be some favor it has to do. Okay, how do we tell that, okay, this tree that we have constructed, is really good, or if this tree that has been constructed is really okay, can be improved? How do we get to know that? Okay, there are certain criterias which we consider. So one among them is the then ID3 search strategy is really based on, like, it selects in favor the shorter trees over longer trees. There's an R missing over here. Please do not mind for that. It selects in favor of a shorter trees rather than the longer trees. Let me give you a very good example. Like, if I have to consider, you just have a single day time and you have to read your textbook and you have to write your exam. Is reading textbook easy, or reading your notes is easy? So which do you find it is more easy? Obviously, it is going to be reading notes, because it's all in a proper manner. It is very easy for you to go, whichever question has been asked to you, you can just give the answer to that. Since you have already read it, it's all very small bits and pieces, so the points are very easy to memorize, so you can write it very well if the notes is given to you. If you have to go ahead with your textbook, you have to read your textbook, you have to make your notes, like, you have to memorize few points that you have to write. It's going to take time. It's not that it is not impossible, but the problem is the time constraint that you have. You feel notes. So the similar way, when you have a tree with 500 nodes, traversing within those 500 nodes is going to be more difficult rather than having a tree with just 50 nodes. If you have only 15 nodes, you can easily go ahead and you can search and you can finish it. Right. So ID3 search strategy normally tells you that shorter trees are really more feasible than a very longer trees. And it is again telling that select trees that place the attributes with the highest information gain closest to the root. This is what we perform. Whichever the attribute has the highest information, we used to consider that, and we used to keep just below the roots. Okay. So just select the tree that places the attributes with the highest information gain close to the root. Yes, this is how the strategy that we followed, right? Because we saw that next, in the next case itself, humidity was a very one, which was telling, okay, this information gain, whatever it is, the highest, okay, we immediately place next near the root. We start constructing it in a similar manner. So there are certain strategies which they tell us, okay, if it is following this is what it is going to be easy for me. So one definition with respect to that is approximate inductive bias of ID3. Approximate inductive bias of ID3 is that shorter trees are preferred over longer trees. We discussed just now. Okay, it's telling that it is very small, right? It is more easy for me rather than going ahead to a longer trees, or the depth of the trees. Okay, small trees are really good. So that is basically with respect to the inductive bias of ID3. Okay, so we will just write that in another way. Okay, a closer approximation of the inductive bias of ID3 is shorter trees are preferred over longer trees. Trees that place the highest information gain attribute close to the root are preferred over those that are not. The same 2 points we have written in the form of a definition, so that it is easy for you when you write it in your exams. Okay, the input of it is the same. Shorter trees over longer trees, whichever has the highest information gain is preferred to be closer to the root. The similar concept applicable. Okay, I think we'll stop here for the day and we'll continue it in the next classes. Thank you so much.